Hello and welcome. In this video, we're going to dive into two core chapters of organic chemistry for AS Chemistry, 9701, Alkanes and Haloalkanes. Our goal is to cover the key concepts you need to ace your exams. So, by the end of this session, you should be able to define and classify these hydrocarbons, understand their physical and chemical properties, describe their reactions using mechanisms, and apply this knowledge to solve exam-style questions. Let's begin our journey with alkanes. Our objective in this section is to understand the structure, nomenclature, and basic properties of alkanes. These are the simplest family of organic compounds. First, the definition. Alkanes are saturated hydrocarbons. The term hydrocarbon means a compound containing only hydrogen and carbon atoms. Saturated means it contains only carbon-carbon single bonds. This means they contain the maximum possible number of hydrogen atoms for their carbon skeleton. They are obtained from crude oil through a process called fractional distillation. This technique works by separating compounds with different boiling points from a mixture. The general formula for any alkane is CnH2n+2, where N is the number of carbon atoms. For example, if N is 1, we get methane, CH4. If N is 2, ethane, C2H6, and so on. This simple formula allows us to predict the formula of any alkane given its name or carbon count. Now let's talk about their physical properties. Alkanes are non-polar molecules because the CC and CH bonds have very similar electronegativity, meaning the electron clouds are evenly distributed. Being non-polar, they cannot form strong intermolecular forces like hydrogen bonds. They only have temporary dipoles which result in weak London dispersion forces. These forces are easily broken, leading to low melting and boiling points. A crucial trend to remember is how these properties change with molecular size. As the carbon chain gets longer, the number of electrons in the molecule increases. This strengthens the temporary dipoles, requiring more energy to overcome them. Therefore, the melting and boiling points of alkanes increase as their number of carbon atoms increases. Now let's delve into the chemical properties of alkanes. Our objective here is to learn the main types of reactions alkanes undergo, which are combustion, cracking, and free radical substitution. Alkanes are known for being quite unreactive. This is because their bonds are very strong. Both the carbon-carbon and carbon-hydrogen bonds have high bond energies, meaning it takes a lot of energy to break them. Furthermore, since these bonds are essentially nonpolar, they don't attract nucleophiles or electrophiles. But, under the right conditions, alkanes do react. The first reaction we'll cover is combustion, which is basically burning. When a hydrocarbon burns completely in a sufficient supply of oxygen, it produces carbon dioxide and water. Here is the general equation for complete combustion. For every mole of C_XH_Y, you get X moles of carbon dioxide and Y over 2 moles of water. The coefficient for oxygen is found by balancing the oxygen atoms on both sides. Let's take propane C3H8 as an example. Balancing it, we get 3 carbon dioxide molecules, 4 water molecules, and it requires 5 oxygen molecules. So the equation is C3H8 plus 5O2 gives 3CO2 plus 4H2O. Now, what if there isn't enough oxygen? This is called incomplete combustion. It's very dangerous. Instead of carbon dioxide, you produce carbon monoxide, a highly toxic gas, or pure carbon, which we call soot. The carbon monoxide binds to hemoglobin in the blood, reducing its ability to carry oxygen. That's why having proper ventilation is critical when burning fuels. Beyond combustion, burning fuels has several environmental consequences. Our objective here is to be able to list and explain the environmental problems caused by the combustion of alkanes. First, we have carbon dioxide, a product of complete combustion. It's a greenhouse gas, meaning it traps heat in the atmosphere, contributing to global warming. Second, carbon monoxide from incomplete combustion, as we just discussed, is a poisonous gas that can be fatal. Third, the high temperatures inside an engine cause nitrogen and oxygen from the air to react, forming nitrogen oxides. These oxides, like NO and NO2, are major air pollutants that can cause acid rain, respiratory problems, and contribute to smog. Finally, crude oil, from which alkanes are derived, contains sulfur impurities. When this fuel is burned, sulfur dioxide is released, which is also a significant cause of acid rain. To mitigate these issues, modern cars are fitted with catalytic converters. This device, made of platinum, palladium, and rhodium, is placed in the exhaust system. It converts toxic gases, such as nitrogen oxides, carbon monoxide, and unburnt hydrocarbons, into harmless ones like nitrogen gas, carbon dioxide, and water vapor. So, while burning alkanes has environmental drawbacks, technology can help reduce the harmful impact. Our next topic is cracking. The objective is to understand what cracking is, why it's done, and the two main types, thermal and catalytic cracking. Crude oil contains a lot of very long alkane molecules. These are less useful and less valuable than shorter ones. Cracking is the process of breaking down these large, less useful alkane molecules into smaller, more valuable molecules. It's essentially reverse polymerization. There are two main reasons for cracking. First, to produce smaller, more efficient motor fuels like gasoline, which contains alkanes like octane. Second, and crucially, to produce alkenes. Alkenes are the building blocks or monomers for many plastics like polyethylene. They are extremely useful in the petrochemical industry. So, what are the two methods? The first is thermal cracking. This method uses very high temperatures, typically between 450 and 750 degrees Celsius, and high pressures around 70 atmospheres. It gives a high proportion of alkenes. For example, a long alkane like C20H42 can crack into a shorter alkane, C8H18, and several molecules of ethene, C2H4. Notice the products contain both alkanes and alkenes. The second method is catalytic cracking. This uses a lower temperature and pressure but requires a catalyst, typically a zeolite like aluminum oxide or silicon dioxide. This method gives a higher proportion of alkanes, especially branched chain alkanes, which are excellent for motor fuel because they burn more smoothly. Here's a common example. C20H42 cracks into C10H22 and C10. Finally, a practical note about the cracking experiment. It's crucial that you always remove the delivery tube from the water trough before you turn off the heat. If you don't, as the apparatus cools down, the pressure inside will drop. This will cause water from the trough to be sucked back into the hot test tube, leading to a dangerous explosion. This phenomenon is called suckback, and avoiding it is a key safety rule. We've seen that alkanes are unreactive, but we've also seen them react with oxygen in combustion and break down in cracking. There's one more important reaction: free radical substitution with halogens. Our objective is to understand how this reaction works and its three-stage mechanism. Alkanes react with halogens like chlorine or bromine, but not fluorine or iodine, in the presence of ultraviolet light. This UV light provides the energy needed to kickstart the reaction. In this reaction, a hydrogen atom on the alkane is replaced by a halogen atom. Let's use methane and chlorine as our main example. The reaction is CH4 plus Cl2 gives CH3 Cl plus HCl. The reaction doesn't stop there. Once chloromethane is formed, it too can react with more chlorine. The hydrogen atoms are successively replaced until all four hydrogens are gone, giving rise to a mixture of mono, di, tri, and tetrachloromethane. In A level, we typically focus on the monochloro product, chloromethane. This reaction is called free radical substitution, and it proceeds via a three-stage mechanism. What's a free radical? It's an atom or molecule with an unpaired electron. This makes them highly reactive. This mechanism is called free radical because the bonds break by homolytic fission. Let's break down the three stages of the free radical mechanism. Our objective is to understand each step: initiation, propagation, and termination. First, the initiation stage. This is where the UV light comes in. It provides the energy to break the halogen bond. In this case, the class Cl bond undergoes homolytic fission. Remember, this means each chlorine atom gets one of the shared electrons. We represent this with half-headed or fishhook arrows. This step produces two chlorine radicals, Cl dot, which are highly reactive and will start the chain reaction. Second, the propagation stage. This is a two-step cycle that continues the reaction. The first step involves a chlorine radical. Since it has an unpaired electron, it wants to form a new bond. It reacts with a stable alkane molecule, methane in this case, to pull off a hydrogen atom. This forms HCl and leaves behind a methyl radical, CH3 dot. Notice that we started with a radical and ended with a new radical. In the second step of propagation, this new methyl radical reacts with another stable chlorine molecule. It pulls off a chlorine atom, forming the product chloromethane, CH3Cl, and regenerates a new chlorine radical. This means a new radical is produced to continue the chain. This is why it's a chain reaction. Finally, the termination stage. In this stage, two radicals find each other and combine to form a stable molecule, ending the chain reaction. There are three possible termination steps. First, two chlorine radicals can react to form a chlorine molecule. Second, a methyl radical and a chlorine radical can combine to form chloromethane. Third, two methyl radicals can combine to form ethane. The formation of ethane is usually in trace amounts because the concentration of two methyl radicals finding each other is very low. This stage effectively mopping up the reactive radicals and bringing the reaction to a halt. Let's test our understanding with a past paper question on this mechanism. The objective is to identify the correct description of the initiation step. The question asks which statement is correct about the first stage of the mechanism, which is the initiation stage. It's asking about the reaction of chlorine and ethane. The mechanism for ethane is identical in principle to methane. Let's look at the options. The initiation step always involves the homolytic fission of the halogen bond. In this case, it's the Cl-Cl bond. So, option A, which states the Cl-Cl bond is split homolytically, is the correct answer. Remember that homolytic fission is the defining characteristic of free radical initiation. Heterolytic fission, mentioned in B and D, is the breaking of a bond where one atom gets both electrons, which is not what happens in free radical reactions. Option C is incorrect because the CH bond is involved in propagation, not initiation. We've covered alkanes. Now let's move on to the second chapter, haloalkanes. Our objective is to understand what haloalkanes are, how they are classified, and how their structure affects their reactivity. Haloalkanes, also known as alkyl halides, are organic compounds where one or more hydrogen atoms in an alkane have been replaced by a halogen atom. The halogens are fluorine, chlorine, bromine, and iodine. A key concept for haloalkanes is their classification. They are classified as primary, secondary, or tertiary based on how many other alkyl groups are attached to the carbon atom that bears the halogen. In a primary haloalkane, the carbon atom carrying the halogen is bonded to only one alkyl group and two hydrogen atoms. An example is 1-chloropropane. In a secondary haloalkane, the carbon atom with the halogen is bonded to two alkyl groups and one hydrogen atom. A common example is 2-chloropropane. And in a tertiary haloalkane, the carbon atom with the halogen is bonded to three alkyl groups and no hydrogen atoms. For instance, 2-chloro-2-methylpropane. This classification is vital because it determines how the molecule will react, which we'll see soon. Let's explore the physical properties of haloalkanes. Our objective is to understand why their boiling points are different from alkanes and why they change with chain length and halogen identity. First, the most notable physical property is their boiling point. In general, haloalkanes have significantly higher boiling points than the corresponding alkanes of similar carbon chain length. There are two main reasons for this. First, haloalkanes have more electrons due to the halogen atom, which leads to stronger temporary dipoles, or London dispersion forces. Second, the carbon-halogen bond is polar. For example, in CCl, the chlorine is more electronegative than carbon, pulling electron density towards itself. This creates a permanent dipole, which allows for dipole-dipole attractions between haloalkane molecules. Both these forces increase the energy required to vaporize the compound. There are two important trends to observe with boiling points. The first trend is that boiling point increases with the length of the carbon chain, just like with alkanes. Again, this is because a longer chain means more electrons, leading to stronger temporary dipoles, and thus more energy needed to overcome those forces. The second trend is that for a given carbon chain, the boiling point increases as you go down the halogen group from F to I. So, an iodoalkane has a higher boiling point than a bromoalkane, which is higher than a chloroalkane, and so on. Let's look at why. If we consider CH3F, CH3K, CH3Br, and CH3I, the bond polarity actually decreases from F to I. So it's not the permanent dipoles. The key factor here is the temporary dipoles. Iodine is much larger and has many more electrons than fluorine. The increase in the strength of temporary dipoles from F to I is so significant that it outweighs the decrease in permanent dipole-dipole forces, leading to an overall increase in boiling point. Finally, let's consider the boiling points of isomers. Branched isomers have a smaller surface area compared to their straight-chain counterparts. This means there is less area for the temporary dipoles to interact. Therefore, branched isomers cannot pack together as closely as straight-chain isomers, resulting in weaker London dispersion forces and lower boiling points. Boiling points decrease as branching increases. We've covered the physical properties. Now let's dive into the chemical properties and the reactions that haloalkanes undergo. This is a very important part of the syllabus. Haloalkanes are much more reactive than alkanes, primarily due to the polarity of the carbon-halogen bond. The halogen is more electronegative than carbon, which gives the carbon atom a partial positive charge, C delta+. This makes the carbon atom susceptible to attack by nucleophiles. Remember, a nucleophile is a species that has a lone pair of electrons and is attracted to a positively charged center. There are two main categories of reactions that haloalkanes undergo: substitution and elimination. First, let's talk about elimination. This reaction occurs when a haloalkane is heated with a hot, concentrated solution of a strong base like sodium hydroxide, NaOH, or potassium hydroxide, KOH, dissolved in ethanol. This condition is crucial. The base must be ethanolic. In an elimination reaction, the halogen atom and a hydrogen atom from an adjacent carbon are removed, or eliminated, from the molecule. This forms a carbon-carbon double bond, producing an alkene. Let's look at 2-bromopropane. When it reacts with ethanolic NaOH, it loses B and H from an adjacent carbon, forming propene. Things get more interesting when the starting haloalkane is unsymmetrical, like 2-bromobutane. Here, there are two different adjacent carbons from which a hydrogen can be removed. Removing a hydrogen from the carbon on the left gives but 1 ene. Removing one from the carbon on the right gives but 2 ene. When this happens, a mixture of products is formed. Zaitsev's rule, which you will learn at a higher level, helps us predict the major product, which is often the more stable, substituted alkene. Now let's explore substitution reactions. The objective here is to understand the first major type of substitution, the formation of alcohols. The conditions here are crucial to distinguish from elimination. For substitution to occur, we use hot aqueous sodium hydroxide, not ethanolic. Aqueous means dissolved in water. The reaction is heated under reflux, meaning the mixture is boiled and condensed back into the flask to prevent the loss of volatile compounds. In this reaction, the nucleophile is the hydroxide ion, OH-. It replaces the halogen atom, which leaves as a halide ion. The general name for this reaction is nucleophilic substitution. For example, 2-bromopropane reacts with aqueous NaOH to form propan-2OL. The exact mechanism of this reaction depends on the structure of the haloalkane. We'll look at the two main mechanisms, SN2 and SN1. Let's start with the SN2 mechanism, which stands for bimolecular nucleophilic substitution. This happens primarily with primary haloalkanes. In this mechanism, the nucleophile, OH, attacks the C delta+ atom from the opposite side of the leaving group, Br. This happens all in one step, through a single transition state. The leaving group leaves, and the nucleophile joins simultaneously. This backside attack causes the molecule to turn inside out, or invert its stereochemistry. Looking at the energy profile, we see a single hump, or transition state. This represents the high-energy, unstable intermediate, where both the OH and Br are partially bonded to the carbon. The primary reason this happens is the lack of steric hindrance around the C-delta plus atom in a primary haloalkane, making it easy for the nucleophile to attack. Now let's examine the other main substitution mechanism which occurs for tertiary haloalkanes. The objective is to understand the two-step process of the SN1 mechanism. Tertiary haloalkanes undergo the SN1 mechanism, which stands for unimolecular nucleophilic substitution. This happens in two distinct steps. The first step, which is the slowest and therefore the rate-determining step, is the heterolytic fission of the carbon-halogen bond. The bond breaks, with both electrons going to the more electronegative halogen, forming a stable halide ion, BRNs, and a planar carbocation intermediate. Why is the carbocation stable? This is due to the positive inductive effect of the three alkyl groups. Alkyl groups are electron-releasing, and they push electron density towards the positively charged carbon, dispersing the charge and making it more stable. This stability is why the carbocation can form at all. Primary haloalkanes cannot form stable carbocations, which is why they don't undergo the SN1 mechanism. In the second step, the nucleophile, Ohio, attacks the carbocation. Since the carbocation is planar, the nucleophile can attack from either side with equal probability. This leads to the formation of a racemic mixture of products if the carbocation carbon is chiral. This step is very fast because the nucleophile is attracted to a full positive charge. The energy profile for an SM1 reaction has two peaks representing the two transition states and a dip in the middle representing the carbocation intermediate. The first peak, corresponding to the formation of the carbocation, is higher. It represents the slowest step. Now, why don't tertiary haloalkanes undergo SN2? The large alkyl groups surrounding the C-delta plus atom in a tertiary haloalkane create what we call steric hindrance. They physically block the nucleophile from attacking the carbon atom from the backside. This steric bulk makes the SN2 mechanism impossible, forcing the reaction to proceed via the two-step SN1 mechanism. So, to recap the substitution and elimination reactions for haloalkanes, remember that the conditions are key. Aqueous sodium hydroxide favors substitution, forming an alcohol. Ethanolic sodium hydroxide favors elimination, forming an alkene. Let's make sure that's clear. Aqueous sodium hydroxide in hot conditions will result in nucleophilic substitution. The hydroxide ion, OH-, replaces the halogen X. This leads to the formation of an alcohol. However, if you use ethanolic sodium hydroxide, in hot, refluxing conditions, it acts as a base and causes elimination. The halogen and a hydrogen atom are removed from adjacent carbons, forming an alkene. The key here is the solvent, ethanol. The solvent changes the role of the hydroxide ion from a nucleophile to a base. Let's apply this to a question. The objective is to correctly identify the product based on the reaction conditions. The question asks for the major product when 2-bromopropane reacts with a hot, concentrated solution of sodium hydroxide in ethanol. The solvent is ethanol, which immediately tells us it's an elimination reaction. Elimination will remove hydrogen bromide from 2-bromopropane. This removes the bromine and a hydrogen atom from an adjacent carbon, forming propene, CH3, CH double bond CH2. Therefore, the correct answer is D. Now let's explore some other nucleophilic substitution reactions. Our objective is to learn how to prepare nitriles and primary amines using haloalkanes. First up is the synthesis of nitriles. Nitriles are organic compounds containing a C triple bond N group. To make them, you react a haloalkane with a cyanide salt, like sodium cyanide, in ethanol, again under reflux. The solvent must be ethanol. If you used aqueous solvent, the hydroxide ion would substitute the halide instead. In this reaction, the cyanide ion, with its lone pair on the carbon, acts as a nucleophile and replaces the halogen. This reaction is important because it's a way to increase the length of the carbon chain by one carbon atom. This means it's a useful tool in organic synthesis for building larger molecules. Once you have a nitrile, you can further transform it into a carboxylic acid through a process called hydrolysis. Hydrolysis means breaking down with water. You can hydrolyze nitriles in either acidic or basic conditions, both requiring heat under reflux. In acidic conditions, the nitrile is converted into a carboxylic acid and an ammonium salt. In basic conditions, it's converted into a carboxylate salt and ammonia, which you then protonate with a dilute acid to get the carboxylic acid. Next, let's look at the synthesis of amines. Amines are derivatives of ammonia, where one or more hydrogens are replaced by an alkyl group. You can prepare them by reacting a haloalkane with ammonia. For this reaction, you need a sealed tube under pressure and heat. Why? Ammonia gas is less dense than air, so it would just rise up a condenser if done at atmospheric pressure, preventing it from reacting. The sealed tube ensures the reactants are kept together. The mechanism is nucleophilic substitution. Ammonia, NH3, acts as a nucleophile, using its lone pair to attack the C-delta plus atom. This reaction forms two products, a primary amine and an ammonium salt. For example, bromoethane reacts with ammonia to give ethylamine and ammonium bromide. So, we've seen how haloalkanes react, but how do we know they are haloalkanes in the first place? In this scene, our objective is to learn the chemical test for the presence of a halogen in an organic compound. The chemical test involves converting the haloalkane into an ionic halide salt, which we can then test using aqueous silver nitrate. The first step is to remove the nonpolar organic solvent you likely dissolved your haloalkane in. You do this by heating it with aqueous sodium hydroxide. This causes nucleophilic substitution, producing an alcohol and a halide ion, X-. Next, it's essential to acidify the solution with dilute nitric acid. Why? To remove any unreacted hydroxide ions. If you don't do this, they will react with the silver nitrate to form a silver hydroxide precipitate, which is white, and could give you a false positive result for chloride. The nitric acid neutralizes the hydroxide ions. Finally, add a few drops of aqueous silver nitrate solution. The silver ions, Ag+, will react with any halide ions present to form a silver halide precipitate. The color of this precipitate tells you which halogen was present. Silver chloride, AgCl, is a white precipitate. Silver bromide, AgBr, is a cream precipitate. And silver iodide, Ag-I, is a yellow precipitate. To confirm your result, you can test the solubility of these precipitates in dilute and concentrated aqueous ammonia. Silver chloride dissolves in dilute ammonia. Silver bromide dissolves in concentrated ammonia but not in dilute, and silver iodide is insoluble even in concentrated ammonia. This allows you to confirm which halogen you have. Let's test this knowledge. The objective is to relate the rate of hydrolysis in this test to the carbon-halogen bond strength. The question describes an experiment where a sample of 1 chlorobutane, 1 bromobutane, and 1 iodobutane are reacted with warm aqueous silver nitrate. This is essentially our test for halides. The reaction equation shown is the hydrolysis of the haloalkane followed by precipitation of the halide. The rate of cloudiness, or precipitate formation, is observed. The fastest rate was with iodoalkane, followed by bromoalkane, and slowest with chloroalkane. The question asks why. To answer this, we need to consider the bond that is being broken in the slowest, rate-determining step. In hydrolysis, this is the carbon-halogen bond. Let's look at the bond energies. The carbon-iodine bond is the longest and has the weakest bond energy, around 230 kilojoules per mole. The carbon-bromine bond is stronger at 290, and the carbon-chlorine bond is the strongest at 350. Since the carbon-iodine bond is the weakest, it is the easiest to break. A bond that is easier to break requires less activation energy and therefore will react at a faster rate. So, looking at the options, option D states that the bond energy of Rx decreases from RCl to Ri. This is exactly what the data shows, and it directly explains why the iodoalkane hydrolyzes the fastest. This is a very common exam question, so make sure you understand it. Let's work through a multi-step synthesis problem to see how these reactions link together. The objective is to design a synthesis route using haloalkanes as intermediates. We want to synthesize 2,2-dimethylpropanoic acid from 2-bromo-2-methylpropane. Looking at the structures, we need to add a carbon atom to our chain and change a halogen to a carboxylic acid. This screams nitrile hydrolysis. Step 1 is to convert the haloalkane into a nitrile. We know this is done by nucleophilic substitution with cyanide. The reagents are sodium cyanide and ethanol, and we heat it under reflux. This replaces the bromine with a cyanide group, giving us 2,2-dimethylpropanenitrile. Step 2 is to hydrolyze the nitrile to a carboxylic acid. We can use either acidic or basic conditions. A common choice is dilute sulfuric acid. We heat this under reflux. The nitrile group -CN is converted into a carboxylic acid group -COOH. This gives us our final product, 2,2-dimethylpropanoic acid. As a bonus, let's consider the mechanism for step 1. The starting material, 2-bromo, 2-methylpropane, is a tertiary haloalkane. Therefore, the reaction with cyanide will proceed via an SN1 mechanism, forming a tertiary carbocation intermediate before the cyanide nucleophile attacks. It's important to be able to identify these mechanisms. We've covered a lot of ground today. Our objective in this final scene is to summarize the key takeaways for both alkanes and haloalkanes. Let's first recap the alkanes. We learned that alkanes are saturated hydrocarbons with a general formula CnH2n+2. They are generally unreactive due to their strong, nonpolar bonds. Their main reactions are complete and incomplete combustion with oxygen, which have serious environmental consequences like global warming and carbon monoxide poisoning. We also saw that long-chain alkanes can be cracked into smaller, more valuable alkanes and alkenes. And finally, they can undergo free radical substitution with halogens in the presence of UV light, which proceeds through a 3-stage mechanism: initiation, propagation, and termination. Now, let's recap the haloalkanes. Haloalkanes are classified as primary, secondary, or tertiary based on the number of alkyl groups attached to the CX carbon. Their CX bond is polar, making the carbon susceptible to nucleophilic attack. This leads to 2 main reaction types. First, nucleophilic substitution with aqueous NaOH forms an alcohol. This reaction can proceed via the 1-step SN2 mechanism for primary haloalkanes, or the 2-step SN1 mechanism involving a carbocation intermediate for tertiary haloalkanes. The rate of hydrolysis depends on bond strength. CI is weakest and hydrolyzes fastest. Second, elimination with ethanolic NaOH forms an alkene. Finally, we learned how to prepare nitriles using KCN in ethanol and then hydrolyze them to carboxylic acids, and how to prepare amines using ethanolic ammonia in a sealed tube. They are tested with aqueous silver nitrate after hydrolysis. This has been a comprehensive overview of alkanes and haloalkanes for your AS Chemistry 9701 course. Remember, practice is key, so go through the past paper questions to solidify your understanding. Thank you for watching.